In the past few lessons, we explored the dimensions of sustainability and the concept of circular economy. But how can we quantify sustainability? Is it important to quantify sustainability for renewable technologies? One of the most powerful tools to assess environmental sustainability is the life cycle assessment, that is LCA. Life cycle assessment is a systematic method able to assess all the environmental impacts originated by the supply of a product or service over its entire life cycle, starting from the extraction of raw materials to its decommissioning at the end of its life. More specifically, for an energy technology, LCA typically includes the entire supply chain, that is, material extraction, manufacturing, construction, energy conversion, operation and maintenance, and decommissioning. The methodology considers both direct and indirect impacts. This means that, for example, in the case of a diesel generator, focusing the attention on greenhouse emissions, LCA takes into account the emission produced by the generator itself. That is considered a direct impact. Nevertheless, there are several indirect greenhouse emissions. Some of them are the emissions due to the energy used for the extraction of the steel used during the manufacture of the generator, the energy needed for the smelting of the steel, the maintenance vehicles, and energy required by the staff for transportation, and the energy needed to extract and refine the fuel. The more indirect the action is, the smaller the impact. Nevertheless, they some can account for a significant fraction of the direct emissions, and this is even more evident in the case of renewable energy technologies because their direct emissions are very low or near to zero. As we mentioned, LCA is able to capture more impacts. In case of energy systems, other examples of impacts that LCA can encompass are the impacts due to radioactive contamination in nuclear plants and emissions of sulfur dioxide and particulate matter in energy systems fed with fossil fuels. But now, let's go into details of the LCA process. The ISO 14044 for the environmental management provide the requirements and the guidelines for undertaking an LCA study. The 4 steps of the process mentioned by the ISO are definition of the scope and goals, inventory analysis, impact assessment, and interpretation. The first step, which is the definition of the scope and goals, lists the motivation, objectives, and especially the boundaries of the study. It also defines the audience of the study. Here, in this first step, it's crucial to define the so-called functional unit in order to define appropriately the function of the system. The life cycle inventory analysis, which is the second step, can be considered as the heart of the procedure as it quantifies inputs and outputs of the system chosen as controlled volume. The approaches available to carry out the inventory include input-output analysis, process analysis, and several further methods that combine all of these techniques and to which we can refer to as hybrid analysis. The common aspect of all inventory techniques in order to obtain the emissions that come from a specific activity is the selection of 2 parameters. The first, the product of an activity level, for example, the tons of raw material used in the manufacturing, and the second, an emission intensity, for example, the emissions per ton of the used raw material. In input-output analysis, special tables called I/O tables are used in order to understand the monetary output from one sector and its relation with the other sectors. Combining these with direct sectoral emissions allow to quantify the emissions resulting from a product or a service. Then, the third step of the procedure, that is impact assessment, allows to assess the combined effects of all the identified impacts of the studied activity or product. Finally, the last step, interpretation, identifies potential issues. For this reason, it includes the sensitivity analysis of the input parameters, the model verification, and of course, conclusions and recommendations. A specific application in renewable energy sources, and more specifically in wind energy, is represented by the selection of the best wind turbine between 2 different types with the aim to minimize the environmental impact in a certain location. The best choice is not such obvious if the size of the turbines is the same. For this reason, the systematic approach of the LCA can support the decision. Moreover, it helps to understand the most impacted life cycle phase. For example, results available in scientific literature obtained with the LCA approach show that the most intensive environmental impact for wind turbine technology come from the nacelle and tower components. This helped designers and researchers to focus on a particular feature of the wind turbine. In addition, the study shows that between two different turbines, one of them has a lower impact on the environment during manufacturing and decommissioning. Finally, we can state that LCA is a valuable tool for decision makers, researchers, and stakeholders for the designing and marketing of sustainable and renewable energy, improving also the social acceptability and trust in these fundamental technologies for the energy transition.